speed or an increase in performance. The last months, I tried to go a bit beyond that and try to understand what benefit occurred. So when is it increased learning? When is it increased speed? And by looking at this, it actually led me to a new benefit of social learning within evolutionary robotics. But I think it's general enough that it will also go beyond. I think it's not only a benefit of social learning in evolutionary robotics or evolutionary robotics per se, but if you have something that you want to optimize where you have parameters, social learning might have an additional benefit that I will explain today. So just a small reminder, why do we study evolutionary robotics? So sometimes it's just not possible or actually irrelevant to hand code a robot, because as a designer you not always know upfront the situation that the robot can be in. And the situation may change. So you want the robot to change their behavior to be optimal again. So this is actually a need for adapting robots that are adaptive in their environments. And to make robots adaptive, we use evolution. We think that's a good method to have as an individual adaptation mechanism for an individual robot. Evolution is known to solve difficult problems, and it can track an on-the-fly moving optimum. But if you want robots to learn new tasks or to adapt, it can still take a lot of time. And we want to speed up this learning process and make it as good as possible. And for that, we use social learning. And we have seen in literature that social learning can increase learning speed and performance. There's a lot of examples, and we also contributed to this literature. And this is not only in evolutionary robotics, but also for the reinforcement learning research area. But when studying all these different papers, there was no generalizable result that said, okay, in this situation you have an increase in speed, and in this situation you have an increase in performance. So we wanted to go a bit further and see if there is something general there, because all these papers have a different simulator, a different robot, a different individual adaptive mechanism. So it's difficult to find from these papers a bit more generalization. So as I said, there's no consensus on the amount of benefits you have. So if you remember a previous white talk, I think it was the last one, I brainstormed a bit about the hypothesis. What could it be? That sometimes it's increased learning speed, sometimes performance. How can you further understand the system? And there, one of the ideas was that it might be due to the system parameters. System parameters are known to influence the performance of a system. So it might also influence the additional benefits that social learning has on top of this individual learning system. So this is what we wanted to investigate, and what we did. So it's still...
What do you mean by system parameters? What would be an example of that?
I will show later on. It will be written. So how did we investigate this? We have 50 different parameter settings for the individual learning mechanism. I will explain later on, but these are parameters for an evolutionary algorithm, such as the mutation rate, population size, etc. Then we rank these 50 parameter sets based on performance. And of course, every parameter setting is rerun a couple of times. So we rank them based on performance, and on the best parameter settings we apply social learning, and on the median performing parameter settings we apply social learning. We'll explain later on which ones these will be. And then we observe the benefits of social learning, so the increase of performance and the increase of learning speed. So still, will not give us a whole general truth of the benefits of social learning, but at least it will be studied in a more systematic way within one simulator. Because all research before only checked one parameter setting and then add social learning. So we go a step beyond by investigating more parameter settings. So what is the task and environment? So First of all, for these 50 parameter settings, we have one robot learning a foraging task. And we do this in simulation because we have a massive amount of experiments. So the foraging task means that the robot needs to collect the puck and bring it to the target area. And when the robot succeeds, this puck is relocated somewhere in the environment. So it can collect more pucks than you see here. So it will do this task for a certain amount of steps. The performance, we call that fitness, that the robot has is the number of collected pucks into the target area. So how does this controller of the robot learns? We evolve it with neuroevolution. So how does that look like? So the controller of the robot consists of inputs, outputs, and a mapping between the inputs and outputs. So in our case, the inputs are wall sensors. Are you close to a wall, yes or no? And it can detect the distance and angle to the closest puck. So those are the input nodes, and based on that, it has to make a decision on the actuators. And in our case, the actuators are the wheel speeds. So it doesn't need to pick up the puck. When it drives over it, it automatically has it. So the output nodes are the left motor speed and the right motor speed. And what we want is a good input to output mapping. So we want to know these connections, which are just weights, just values, real values. And, well, this is called just a simple feed-forward neural network, but we advance it a bit with extra hidden neurons, which can also evolve over time. So we don't want to set up front, to tell the robot up front, this is your ideal controller, this is the ideal number of hidden nodes and hidden layers. No, that can evolve by itself. This is a method called NEAT, Neuroevolution of Augmenting Typologies. So how does this learn then on this one robot? Well, we start with a population of these controllers that we randomly initialize. So all weights are randomly initialized. Each neural network is tested for that certain amount of time steps where it can collect those pucks, and it gets a performance, and you have your population. Based on that population, the performances, you can select parents. You do that with a tournament selection. When you have those parents, you recombine these weights and typologies in a smart way, because they can have different typologies, so NEAT helps you to ensure that you have a good recombination method. You can apply some mutation, add some nodes, or change some weights extra. And then you have offspring that you reevaluate again, and then you, in our case, we replace the whole population with the offspring. But of course, you can have different methods there too. So, to show you in video, this is not the research that I will explain further on, but just to show you how a robot evolves. I have this video where it is evolving just obstacle avoidance, so just avoiding the wall. So first generation, individual one, I think we had 10 here per generation. This is that random controller that is just trying something for a certain amount of seconds. So here it's not really smart, it's the first individual, the first generation. Well, here we see the second one kind of has different weights, but the behaviors is apparently a bit similar. So for this first generation, all individuals, you just list their performance. And here, the performance is 0, because it's turning too much. So the fitness for the obstacle avoidance is, are you driving straight, are you not rotating, and are you not bumping into the wall. So you do this after the first generation, you recombine and create offspring. And you have your second generation, do that again and again. And if you evolve this for a bit amount of time, for example, generation 15, you see that it's already going around in the environment a bit, but it's still bumping into the walls. So the fitness is accumulated over time. So every time step it can get points. And your total fitness is adding that all up together. So you see in generation it's 30, it's doing quite well already. Sometimes it will still bump into the wall because it is that adaptive mechanism. So it's still trying out new things. You still have that mutation. So it's okay if it still bumps into the wall sometimes. So if this robot is now individually learning, how do we apply social learning? Well, for social learning, we have one robot in their separate environments. We do this to not be influenced by the collisions of the robots in the arena. So if you have more robots in an arena, if you want to study the effect of more robots doing social learning, if you all have them in the same arena, you have to make sure that your statistics are not influenced based on all these collisions of the robots. So that's why we observe them in isolation. In this case, the pucks are on the same location, but that is not, that doesn't have to be the case. It can be everywhere. So what happens? Every robot learns individually, goes through this whole generation, and then at the end, it can exchange their best controller. And you incorporate the controller of the other one, the best one. If it's better than your worst one. So usually you do incorporate it. And to also take into account the amount of time you give the robots in total, you want, if one robot is learning for 1 hour, you want 2 robots to learn for half an hour. So this is, how we do this is to divide the population size of one robot between multiple robots. So if you have a population size of 100, if we study 2 robots, they both get a population size of 50. If you study 4 robots, they would get 25. Okay, so now you have all the details how the robot is learning. So just a small recap of the experiment we actually did. So we have 50 parameter settings. So that's the population size, mutation rate, possibility to add a node, all these different neat parameters, which are too many to list. We give them to one robot learning, and we rank them. So parameter setting 1 to 50 is ranked based on their fitness, their average fitness over multiple runs. Then we call parameter setting 1 to 10 the best settings, and parameter setting 20 to 30 the medium parameter settings. And for those settings, we apply social learning. Social learning for 2 robots and social learning for 4 robots to kind of already see the influence of adding more robots. And then we look at the different benefits of social learning. So, going into the results. Here we see the rank of the different parameter settings, 50 in total, and the number of pucks collected, so the performance. This is the average performance over 20 runs for a particular run. The rank 1 to 10 we call the best, and 20 to 30 we call the median. We didn't investigate the influence of social learning on the other ones too. We could, but we haven't so far. So we do see that the parameter settings are quite important for the performance of the individual robots. This is of course logical because, for example, if you shut down the whole mutation, then the system might have more trouble to evolve. We know that mutation is a good factor in optimizing. So this is okay. So this is also why we didn't do setting 40 to 50 to apply social learning, because maybe just those parameters are just too way off to apply social learning. So we only take 1 to 10, 20 to 30. So if we study the benefits of social learning, then I'm talking about the increase in performance and the increase in learning speed. I will visualize them first in a graph so that you know what we mean if you then see the graphs. Oh, here I have a video that you can see. It's actually picking up bugs and going to the target. So what are the measures we looked at when we look at the benefits of social learning? Well, if you have one robot only, we usually, in evolutionary robotics, or in general, we have a performance over time. Time can be number of generations or number of evaluations, which is number of evaluations is usually, we have in our system 1 evaluation per robot, and we have a certain population size in the generation. So for us, the time scale is the number of evaluation, and we look at the performance. So if you look at performance, it's logical. You can look just at the end performance when you stop your evolution. For learning speed, you can define many different things. We chose this particular measure where we look at what is the time that we reached 80% of the final observed performance. This is what we call T80%. And we have the T100%, and then we said, okay, the learning speed, it's kind of more like a convergence measure. You divide the time you have of 80% divided by the total time, and then 1 divided by that again. So if you have a high learning speed, it means that you converge really soon already. So what do we measure if we have more robots? So performance, I think, kind of logical. You observe the end performance for more robots and the end performance of one robot, and you just divide the multiple robots by the one to have some kind of performance ratio. For the learning speed, we looked at the time it took for more robots to have the same 80% performance of the one robot. And we divide those two values. So let's then observe some effects of social learning. What do we see on the left? We again have the rank. So we only have results for rank 1 to 10 and 20 to 30, the best and the median settings. And the performance ratio is the end performance for multiple robots divided by one robot. The blue ones are for 4 robots, and the red ones are for 2 robots. So we do see a trend here. We see a trend that if the parameter setting is worse, the relative increase of social learning is higher. There is here a significant correlation between the rank and the performance ratio of about 0.6. When we look at the speeds, we kind of see a similar trend, but it's not significant. So we actually see that usually if you add more robots, there is an increase in learning speed. But what we also see overall, it's quite volatile between the parameter settings. You kind of see a cluster here that it is better, but some dots are still worse if you do social learning. So we do see that it's really volatile in the same setting, just a different parameter set. So if you study in isolation only this point, you might say, well, social learning has no benefits. And if you studied this parameter setting, then you say, oh, there's an increase of 50%. So now we kind of better understand the problems in the literature. But we do see overall that the median parameter settings benefit more from social learning. If we visualize this in another way, when we look at the absolute performance of the learning speed, the learning speed was that rate of convergence. So here we see, now the blue is the median setting and the best setting. And we see that, of course, the median settings score lower in the performance, number of bucks collected. But there's also really a separation between the ones that are still learning, so they're just learning slow, and the ones that are already done learning. So the curve is already converged. So what if we apply, so we did apply social learning also on this set, but what if we visualize it in a different way, the learning speed of bucks collected? Then we actually see that the best absolute performing parameter setting is now one of the median settings where social learning is applied. So in the end, with social learning, you get a higher absolute performance in this case. And we also see that these dots that the blue dots moved to the right, but also are not converged anymore as fast. So social learning can reduce this convergence and in the end results in the highest absolute value. So to conclude, some important takeaways. So the benefits of social learning are really, really dependent on the parameter settings. That is what we've seen. In general, the median parameter settings benefit more from social learning. But we also saw that social learning reduces the sensitivity to the choice of parameters. Because if you have median parameter settings and you apply social learning on top of it, you see that you couldn't distinguish the median parameter settings from the best anymore. So, in a system, you could say, okay, if you have a one robot learning, you could say, okay, I can tune my parameters maybe, or I can just apply social learning And it can be seen also maybe as an alternative to tune the system. So this is our extra benefit that we saw when we studied the benefits of increased performance and increased learning speed. And that was it. Are there any questions?
You just said that social learning might be an alternative to other types of tuning. What would be the benefit of using social learning as opposed to other ways of tuning?
It will be computationally less expensive, because if you would tune this individual learning system, you need to test different parameter sets. Now we started with 50, but then you didn't tune it yet. If you do social learning, you only have to do one system. And you know, kind of, because if you have your system, it's usually not tuned yet. So you kind of can assume that you have some kind of medium performing parameter setting. So then we know what we've seen here, that results in the highest benefit in terms of performance and learning speed. So it might, if you don't have the time to tune your system, but it's easy to make it a multi-agent or a social learning one, you could use that. Yeah. But it's not a strong conclusion yet, it's only maybe.
Can you maybe explain again what you mean by social? For example, and how it differs for just having more individuals. For example, in humans, if you team up in a win situation, and there's added value because of the dialogue happening between two humans, more reflection, and therefore they may learn better. It, for example, could be an argument. I'm wondering if, in this case, it is just the multiple agents being there, so it goes quicker, or is there really also a mechanism that sort of how they interact? Or
so they both have their own environment, so it's not a collaborative task. They really learn individually, and they sometimes get a best controller of the other. So I think what it could be is you get some new knowledge from the other, you get some novelty, some other parameters that influence new parameters that you test again. So it's kind of an increase in diversity, just an extra adaptive mechanism. So if you have an individual robot, it adapts still to having that mutation and recombination. And with social learning, you just have an extra source of getting new types of information.
Is it then to say that it's just, let's say, more individuals, and there's no special way of communicating?
They do communicate. They communicate their controller, their best controller. Yeah. So they're the weights from the inputs to the outputs. And that they use to create new controllers. So if you look at the individual, a robot execute this evolutionary algorithm by itself. But if you do social learning, you get an extra good parent, a high-performing parent from the other that takes place into the recombination of mutation operators. So you have different controllers that you test compared to when you're alone. And apparently this helps sometimes, depending on the parameter setting.
Okay, thank you.
So, does this mean that, this island model kind of type of GA, is it in a way quite similar? And it's also kind of a way of enhancing diversity?
So a really interesting thing to test would be comparing this model with just an island model within one robot. I've done some initial tests for that. I couldn't really find anything yet, but definitely, yes, I think this is this might explain some things, yes. So then the key is just increase the diversity. Yeah.
Could be interesting to maybe try with another diversity enhancing approach as well.
Yeah.
Did you make some analysis on what parameters are beneficial for social learning? And what is the correlation?
Yeah, we did do a regression model on the performance of the parameter set and all the different settings. We did do that, and from need, I think need has 23 parameters or so, and I think only 6 were significant for the regression model. So we're also now tuning further with only those parameters that are significant. But the most important parameters were the mutation probability. I think it was lower. The lower the better it was there, but of course it has some lower boundary. And the increase in population size. Those were most important.
What do you mean increase in population size?
So the regression model said that it's best for the system if you have a high population size, but not too high mutation probability. But we also have to look into this a bit further if this somewhere is comparable to this island model hypothesis.